Look, our planet has a bit of a fever, and a big reason for that is carbon dioxide, or CO2. We put tons of it into our atmosphere every single day from things like driving cars, making electricity, and constructing our buildings. All that extra CO2 acts like a thick blanket, trapping heat and warming up our world. This is climate change, people. It's a huge challenge, and to solve it, we need some seriously cool and innovative ideas. We can't just stop making CO2 overnight, so we also need to find clever ways to pull it right out of the air. It's a big job, but science and engineering are on the case, and the solutions are getting really interesting. So, what if our buildings could help us fight climate change? What if the very walls around us could breathe in that extra CO2, just like a plant? Well, a brilliant team of scientists at ETH Zurich has developed something that does exactly that. It's not just a material, it's a living material. Think of it as a biological superhero for our cities. This isn't some far-off science fiction idea. It's happening right now. We're talking about a substance that is alive, that is smart, and that we can use to build things. It's a fundamental shift in how we think about construction and our environment. This incredible new material is a special kind of hydrogel, which is a fancy word for a jelly-like substance that holds a lot of water. But this isn't just any jelly. It's infused with living, breathing microorganisms. Specifically, it contains a type of bacteria called cyanobacteria. These tiny powerhouses are what give the material its magic. The whole mixture is designed to be printed, kind of like using a 3D printer. This means we can create complex shapes and custom building components, like bricks or facade panels, that are literally alive and ready to get to work, cleaning our air from the moment they are made. The potential here is just staggering. Imagine entire building facades that actively scrub the air, reducing the carbon footprint of our cities block by block. We're moving beyond passive, less bad buildings and into the realm of active, positively good structures that contribute to healing our planet. These living materials could be integrated into new construction or even used to retrofit older buildings, turning our urban landscapes into giant CO2-hungry forests. This is the kind of forward-thinking science that gives us hope. It's engineering meeting biology to create a better, cleaner, and cooler future for everyone on this planet. Consider the facts, and you'll see it's an amazing development. So, what exactly makes this material live? The secret ingredient is a specific type of cyanobacteria known as Synechococcus. You might know their cousins, algae, but these guys are special. They are some of the oldest life forms on Earth, and they are absolute masters of photosynthesis. Photosynthesis, you'll remember, is the amazing process plants use to turn sunlight, water, and carbon dioxide into energy and oxygen. These bacteria have been doing it for billions of years, and they are incredibly good at it. They are tiny, single-celled organisms, but when you get billions of them together in this special hydrogel, they become a powerful force for good. The hydrogel itself is a critical part of the system. It's not just a passive container, it's an engineered habitat. It's designed to provide the cyanobacteria with everything they need to thrive: water, nutrients, and protection. The gel is also transparent enough to let sunlight through, so the bacteria can get the energy they need to perform photosynthesis. It's like building the perfect little apartment complex for trillions of tiny, CO2-eating tenants. This combination of a living organism and a custom-built supportive material is what makes the whole thing work so well. It's a true symbiosis between biology and material science. One of the most exciting things about this living material is that it's printable. Using 3D printing technology, scientists can extrude this bacteria-infused gel into almost any shape they can imagine. This opens up a world of possibilities for architects and designers. They can create lightweight, intricate structures that are optimized for both aesthetics and carbon capture. This printability means we can produce these living building components on demand and with very little waste. It's a much more sustainable way to think about manufacturing parts for our homes and offices, moving us away from energy-intensive processes like making cement and steel. The material is also resilient. The cyanobacteria are tough little critters. They can survive in a wide range of conditions, including the low-light environments you might find on the side of a building in a dense city. This robustness is key for real-world applications. You can't have a living wall that gives up the ghost the first time there's a cloudy week. These bacteria keep working, diligently pulling CO2 from the air day in and day out. This durability ensures that a building made with these materials will continue to be an active part of the climate solution for a long, long time. Now for the really cool part, how this material actually captures CO2. It doesn't just do it in one way, it has a two-pronged attack. The first method is the one we've been talking about, photosynthesis. Just like any plant, the cyanobacteria inside the gel absorb CO2 from the atmosphere. They use the energy from sunlight to break down the CO2 and use the carbon to grow and multiply. This process creates what we call biomass. Essentially, the carbon that was floating around in the air as a gas gets locked up in the form of new bacterial cells. The material literally gets denser with captured carbon as it lives and grows. But wait, there's more. These particular cyanobacteria have another, even more amazing trick up their sleeves. Through their metabolic processes, they can encourage the formation of calcium carbonate. That's a solid mineral, the very same stuff that makes up limestone and seashells. The bacteria change the chemistry of the immediate surroundings within the hydrogel, which causes calcium ions present in the gel to combine with the captured CO2 and form these tiny, stable mineral crystals. This process is called biomineralization, and it's an incredibly effective way to lock away carbon for the long term. It's not just storing it, it's turning it into rock. This second mechanism is a game changer because it provides a very durable form of carbon storage. While the carbon stored in biomass could eventually be released back into the atmosphere if the bacteria decompose, the carbon locked away in calcium carbonate is stable for thousands of years. It's mineralized, it's solid, it's not going anywhere. So, our living material is not only capturing CO2 through growth, but it is also petrifying it, turning a problematic gas into a harmless, stable solid. This dual-action capture makes the material exceptionally efficient at cleaning the air around it. Think about the life cycle of this material. As it lives, it actively removes CO2. Over time, it slowly hardens as more and more calcium carbonate is formed within its structure. Eventually, you could end up with a building component that started as a soft, living gel and transformed into a solid, carbon-negative brick. It's a beautiful example of how we can use natural processes, perfected over billions of years, to solve modern problems. We are essentially accelerating a geological process, using tiny living factories to build our way to a more sustainable world, one mineralized carbon atom at a time. This isn't just a cool experiment stuck in a laboratory. This revolutionary material has already been put to the test in the real world, showing everyone what's possible. One of the most prominent showcases was at the Venice Biennale of Architecture, a world-renowned event where the future of building is put on display. There, an installation called The Living demonstrated how the material could be used to create structures that interact with their environment. Visitors could see with their own eyes a building component that was alive, breathing, and changing over time. It was a powerful statement about the future of architecture. The material also made a splash in Milan, another hub of design and innovation. As part of an exhibition, a prototype facade was constructed, showing how these living panels could be integrated into the skin of a modern building. These public demonstrations are so important. They take the science out of the academic journals and put it right in front of people, helping everyone, from architects to city planners to the general public, imagine what our future cities could look like. Seeing a wall that is green, alive, and cleaning the air is a much more powerful experience than just reading about it. The choice of cyanobacteria is central to this success. These organisms are photosynthetic superstars. They are more efficient at converting sunlight into energy than many terrestrial plants, meaning they can capture more CO2 in a smaller space. Plus, their ability to thrive in low light and to trigger mineralization makes them uniquely suited for the job of a living building material. They are nature's perfect little carbon capture machines, and scientists have now given them a new home where they can do their best work on a massive scale. It's a fantastic example of biomimicry, learning from nature's genius to solve human challenges. So what does this all mean for our future? It means we are on the cusp of a revolution in construction. We can begin to dream of and build cities that are not just consumers of resources, but active contributors to environmental health. Imagine buildings that purify the air we breathe, reduce the urban heat island effect, and turn a global problem like CO2 into a useful resource. This living, breathing, carbon-eating material is more than just a new type of brick. It's a symbol of hope. It's proof that with ingenuity, creativity, and a little help from some of the oldest life on Earth, we can build a better, brighter, and greener world.